welcome to this video on hypothesis testing. So, this is the second part of hypothesis testing. This is where we're actually looking at full A-level style questions. The first part is definitely required to get to this stage. Do make sure you watch that. So the first thing we're going to be looking at is doing one full hypothesis test. So this is exactly how they'll come up in the A-level. Maybe with some extras with your definitions and things like that. But let's have a look at this one then. So John tosses a coin 8 times. And it comes up heads 6 times. He claims that the coin is biased towards heads. With a significance level of 5%. Test his claim. So it stays here, step 1 is to define the test statistic. So in this case, our test statistic is X. And we're looking at the fact that X is the number of heads. That's what we're looking at here. So X is the number of heads. We also know that it's a binomial distribution. So we're going to say that, so I've just changed my pen. So P is the probability of getting heads. P is equal to the probability of getting heads. And we know that it's a binomial distribution. So X is a binomial distribution. And how many times has he done that? He's done it 8 times. And P is the probability of getting heads. So that's where we're starting here. So remember, a hypothesis test is looking at 2 different things. The null hypothesis, which is your original hypothesis. In this case, it's that the coin has got a 50-50 chance. So it's going to be 0.5 of getting heads. However, we've also got an alternate hypothesis in which John's claims that actually this coin is biased towards heads. So we define our null hypothesis first. So our null hypothesis, H0, is that the probability is equal to 0.5. So that's our null hypothesis there. The next one is the alternate hypothesis, which is John's hypothesis. And John is saying here that he thinks that the coin is biased towards heads. So that means that the probability is going to be greater than 0.5, because remember, this probability is the probability of actually getting a head specifically. Okay, we've defined that up here. So P is the probability of getting a head. So we've got our null hypothesis, we've got our alternate hypothesis, and we've also got a test. So we've done our test here. And the test was that he did it 6 times and he got 6 heads. So we are going to assume that H0 is true. So we're going to say that we've got a distribution with a binomial with 8 different trials, and we've got a probability of 0.5 there, like so. So because we are looking at the fact that we're getting a head more than 6 times, this is what we were trying to find. We're trying to find the probability that X is greater than or equal to 6. Now, we already know that this is the same as 1 minus the probability of X being less than or equal to 5. So we've got to use our calculator to find the probability of it being less than or equal to 5 now. So let's just use our calculator. Now, we don't need to use the list on this because we're only looking at one specific value, and our significance level is 5%. So if the probability of this is less than that 5%, then it means that we can reject the alternate hypothesis and accept the null hypothesis. So it's saying, actually, the probability is still too high, so the alternate hypothesis isn't true, and the null hypothesis stands. So in this case here, we're trying to find this one now. We were doing lists before to look at the critical regions, but in this one here, because we're only looking at one of them, I can go to distributions. I can go to, where am I going? Distributions, binomial CD, like so. Let's get that up there. Binomial CD, but I only need in this one, 1 variable. So I'm looking at 2 in this case. So I'm saying that I've got a binomial distribution with plus on there for some reason. So a binomial distribution, CD, cumulative distribution, variable. So I've got a binomial distribution here okay, with 5 is what I'm looking at. So I want everything that's less than or equal to 5. I've got a distribution with possible of 8 different outcomes, and the probability is 0.5. So here I put those 3 things in. Okay, so x is equal to 5 in this case. N is equal to 8, and the probability is equal to 0.5. Press equals on that. Now I get a probability here of 0.8554. So it's going to be equal to 1 minus 0.85547, we'll say. I can just do 1 minus all of this in the calculator. So, menu 1 minus, the answer is equal to 0.144. So it's actually 0.145. So 0.1445, it says here, 445, which is equal to 14.45%. Now, we've found that the probability of getting 6 or more is equal to, for this distribution, is 14.5%, but we set our significance level as 5%. So because this is greater than 5%, it's saying here that actually the probability of this is far too high for our significance level, so it means that there is not enough evidence to reject H0. So as, and let's make this really clear, as 14.45% is greater than 5%, there is not enough evidence to reject H0 and accept H1. So there's not enough evidence to say that the coin is biased towards heads. And it's worth stating that as well. So the coin is not biased. Brilliant. Okay. So we've looked at loads. That's a full hypothesis test looking at this now. So the X is the probability of getting the number of heads. Okay, P is the probability of actually getting heads. We're doing a binomial distribution. Okay, we're saying that our null hypothesis, so my original hypothesis is 0.5. John is saying that he thinks his coin is biased towards head because he got 6 heads. Here we've got, we're going to assume that our original hypothesis is true, find out the probability for that, which in this case is 14. But actually this is greater than our significance level, which we set at 5%, which means there is not enough evidence to reject H0 and accept H1, so the coin is not biased. Let's just check all of those there. So that's our first part. So I'll make this big for you so you can see it. So X is the number of heads. P is the probability of heads. We've just gone through all of this. We didn't use the binomial table. We used our calculator. That's fine. Okay. So let's have a look. There is another way we can do this, and actually we look at this one now. So so here we used probabilities to look at this, but we can also use critical regions, which is what we've looked at before. So let's have a look now at this with a critical region. So if X is the number of heads, P is the probability of heads. We've already got our null hypothesis, which in this case was that H0 is equal to 0.5. We've got our alternate hypothesis, which is that the probability is greater than 0.5. This is what John is saying. So first of all, we've got to find the probability of, we've got to find our critical region. So we're looking for the first time that our values go into the 5%. So with this, take note, this isn't an extra part. We've already proved it. This is just another way of showing it. So we're saying instead of looking at the probabilities this time, we'll actually look at how many heads means that this coin is biased. So we're looking at two different things here. So instead of this, we're going to go back to looking at the table. Now they've already got the table on here. I'm going to give you a reminder of how to use that table. So we go to 7, which is distributions on here. Try to make sure you can see that. So there's a 7 on there, brilliant. We're going to binomial CD, which is there. Menu, binomial CD, top one there. And then this time we're not looking at just one variable, we're looking at the list. We're looking at all of these here, okay? Now, because we know that the probability is equal to 0.5, and we've got 8 different, we've got 8 opportunities of that happening, then we know that the expected value is going to be 8 times 0.5, which is 4 in this case. So I'm going to start on my list from, because there's only 8, I'll start from 4. So, and because we know it's going to be greater towards heads, so it's going to be 4, 5, 6, 7, and 8. Press AC on that, then press equals again. Okay, then it's going to come up with your binomial. So we know we've got 8 different outcomes. We've got a probability of 0.5 on there. So let's press that. And remember, we're looking for the first time that it goes over, in this case, 1 minus our significance level, which is going to be 95% or 0.95. And then we're going 1 above that, because remember the probability is 1 minus the one which is below that. So the first one which goes above in this case is equal to 6. We can see that from this from our list here if you need to look. So 6 is the first one that goes over 95%, which is 1 minus our significance level. So in this case, it's going to be, we go 1 above that. Remember, we always go 1 above. So for probability of x being greater than or equal to 7 in this case is equal to 1 minus the probability of being less than or equal to 6. We know that the probability of being less than or equal to 6 is this one here, which is equal to 1 minus 0.9648. So let's do that. So 1 minus 0.9648, which is equal to 0.0352, which is equal to 3.52%. So this one here is the first time that we go into our critical region. So we've got to make that really clear. So remember, our significance level was 5%. This is less than 5%. It's the first time that it goes below 5%. So our critical region is critical region is that x is greater than or equal to 7, which is this part up here. So instead of looking at the probabilities now, remember we're looking at the amount of heads that he actually got. So we're saying that the critical region is when it's 7 or above, okay? So it's greater than or equal to 7. However, John only got 6 heads. So in this case, 6 is not in the critical region. Six is not in the critical region, so we do not, again it's the same process, isn't it? So we do not reject H0, and there is not enough evidence to accept H1. So we do not reject H0, and the coin is not biased. Brilliant. Okay, so we've just done that in a different way. We're looking at now the actual values of this instead of the probabilities. So here, let's look at this one. So they've worked out the critical region, which we said was x is greater than or equal to 7. Remember, we're looking for the first time it goes past, and then because it's discrete, we've got to do 1 minus the one which is below that, which is, so we've got to go to the one above. So the probability of 7 is greater than or equal to 0 is equal to the probability of 1 minus 1, which is less than or equal to 6. So in this case, our critical region is greater than or equal to 7, but 6 is not in the critical region, so we do not reject that hypothesis. And that's that first question. That's a full question there. Now, we've done that in 2 different ways. We didn't need to do it in 2 different ways, and I've done a lot of explaining. So it did take a bit of time. But let's have a look at another one. Let's move on to our next one. So, in fact, it is worth talking about this, actually, because this one doesn't actually come up in the book, but it does come up in past papers. So Sheila wants to know if a coin is biased towards heads and throws it a large number of times, counting the number of heads. The p-value is less than 0.03. Conduct the hypothesis test at a 5% significance level. So with this one here, all we're looking at is basically they're telling you this last little part. So they're telling you here our p-value was 14%, 14.45%. Now, in this one, they're just cutting that out. So they're telling you that the p-value is equal to 0.03. So with this one here, again, we've got to state everything that we know. So I'll make this big for you so you can see it first, actually. Give you a chance to get it down. Okay, so the first thing we do is we say that the P is the probability of getting ahead. So P is probability of getting heads. So P is the probability of getting heads. Okay. We say our null hypothesis, and our null hypothesis in this case, so H0, is that the probability is equal to 0.5. Sheila wants to know whether it's biased towards heads. That means the probability of heads is going to be greater than 0.5. She throws it a large number of times, and she actually gets a p-value of 0.03 with a significance level of 5%. So straight away, we can just say that 0.03 is less than 0.05, which is our significance level. So with this one here, so because this is equal to 0.03, that means that we're in that critical region, doesn't it? So that means we are less. This was our critical region. Sorry, this was our significance level. We're at 0.03, which means I'm below my significance level, which means that I'm in the critical region. So this means, we reject H0. We reject H0. And we accept H1, which means that actually, because my probability of this, the chances of this happening from her test are below 0.03, it means that there is significant evidence to suggest that the coin is biased. So there is significant evidence spelling evidence wrong, don't I? Evidence to suggest the coin is biased. Brilliant. Okay, so here she's done her test. We've got a really low probability from our experiments, so that means that we say we can reject H0 and accept H1, which means that this coin is there is significant evidence to suggest the coin is biased. Now, it doesn't actually mean that the coin is biased, okay? Now, you just got to be careful of that, just saying that there's significant evidence. So actually, because it's really, really unlikely to happen, it means that actually there is a good chance that this coin is biased, okay? So let's have a look at another one of these. I'll make this big so you can see it. So the standard treatment for a particular disease has a 2/5 probability of success. A certain doctor has undertaken research in this area and produced a new drug which has been successful in 11 out of 20 patients. The doctor claims that the new drug has an improvement of the standard treatment. Test at a 5% significant level the claim made by this doctor. So, looking at this one here, let's go back to what we said. We've got to, first of all, define X. So, define our test statistic in this case. So, remember to make sure you're getting this down in your notes. Remember, the only way to learn maths is to do it. Okay? So, our test statistic in this one is that X is the number of patients for who the trial was successful. Okay, so X was the number of patients for who the trial was successful for. Okay, now P is the probability of success of each patient. So that P is the probability of success. Okay, that's what we're thinking. And we know that X follows a binomial distribution. Now we're looking at here, it says she does a test with 11 out of 20 patients. So it's going to be of 20 patients, and we don't know the probability yet. Well, we do, we're going to assume the probability, but we put P for now. Okay, so we have to set all of this out. You will get marks for these. So X is the number of patients for which the trial was successful for. Okay. P is the probability of success, and X follows a binomial distribution with 20 patients, okay? So, the next thing we need to do is state our null and alternate hypothesis. So in this case, our null hypothesis is that our probability is equal to, now our probability in this one was 2/5, so 2/5. We're going to write as a decimal because we're going to type into here, so that's equal to 0.4. Okay, so our null hypothesis, so our original hypothesis is that the probability of success is equal to 0.4. So our alternate hypothesis is that we actually think that the probability is greater than 0.4. Okay, so we actually think here that our chance of success is higher. Now, this makes sense because what we're saying here is we've got this new treatment, okay? The doctor's made this new treatment. He thinks that it's more successful. So here we're saying that the probability of this happening is 0.4 because we want these people to get better, don't we? That's what the doctor's made this new drug for. So we've got our null hypothesis. We've got our alternate hypothesis. And now he's done a test with 11 out of 20 patients. So we're looking here now at the probability or the chance of this happening if our null hypothesis was true. So we assume that H0 is true. We assume that H0 is true. So we're going to say here that X follows a binomial distribution with 20 patients and a probability of 0.4. Okay, that's what we know. And we're looking here, we've got 11, the drug was successful for 11 out of the 20 patients. So we're going to say we want the probability of X being greater than or equal to 11. And we know this is going to be equal to 1 minus the probability of X being less than or equal to 10. Like so. So we go back to our calculator. We go to distributions, which is 7. We're going to go to binomial CD, which is 1 in this case. We only need to look at 1 here, so we're only going to go to a variable. We're setting x to be equal to 10, less than or equal to 10. Our number of patients was 20. And our probability in this case, we're assuming the null hypothesis, which in this case is 0.4. And here we get a probability here of 0.8724. So it's going to be 1 minus 0.872479, it is there. So we can go menu, 1 minus the answer there, which is equal to 0.1275. So actually, our probability, which is equal to 12.75%, okay? So, what is this telling us? Well, this is telling us that actually there's not enough evidence because we set our significance level at 5%. So we're saying here that, now this is the important part. So 12.75% is greater than 5%. Okay, so there is not enough evidence to reject H0 because actually I'm not in the critical region, so there's not enough evidence to say this is true. So there is not enough evidence to reject H0. There's not enough evidence to reject H0. So, therefore, this just means that the new drug is potentially the same as the old drug, or there's no improvement. So, therefore, the new drug is no better than the old drug. So the new drug is no better than the old drug. Okay. Now, this makes sense here because what we've got is we've got this 5% here, and we're saying that actually the probability here is 12.75%. So it's not in my critical region, which means that although looking at this probability, 11 out of 20 patients, that there is a probability, so 11 out of 20 is a probability of 55%, just because the probability is higher than my original probability for the new drug, it doesn't mean that this new drug is better, because it could have just been chance that more people were successful with the treatment in that particular trial. You'd have to do even more trials, or you'd have to create a new drug in this case, or develop it further. But in this case, there is not enough evidence, because with a probability of 0.4, actually there is a good chance that we could get 11 patients who get it right. Okay, so that's that next question. So that's our next example. So let's just check those answers. Let's get them big so you can see them. So the number of patients for whom the trial is successful, the probability of success in each patient, we know it's following a binomial distribution. Our null hypothesis was that the probability was equal to 0.4. Our doctor has made a new drug and he thinks it's more successful because he's had more patients with success, so in which case that was going to be equal to greater than 0.4. We assumed it was true, and then we had a look at the probability of that happening. We got a probability in this case of equal to 12.75, which means that the drug was no better than the old one. So we've had a look at 2 examples now. So we're going to be looking at a past exam question now. So let's have a look at this one. Now it's probably worth you pausing and have a little go at this one yourself. See whether you understand it. See whether you know all the steps. Notice there's 6 marks in this. So there's quite a few marks. So pause now and have a little look at that yourself. So I'm going to go through it now. A student takes a multiple choice test. The test is made up of 10 questions, each with 5 possible answers. The student gets 4 of the questions correct. The teacher claims that she was guessing the answers. Use a one-tailed test at a 5% significance level, whether or not there is evidence to reject the teacher's claim. Okay, so state your hypothesis. So the first one is that the first thing we need to think about is the fact that there are 5 possible answers here. So what's the probability of actually getting one of them right if you are guessing? Well, the probability of getting one of them right if you are guessing is going to be 1 in 5, which in this case is going to be equal to 0.2. Now, that's quite difficult to understand that. So it's a tricky bit to start. If the student is guessing, what's the chance of them getting it right? Well, the chance of them getting it right is going to be equal to 0.2. So the test is made up of 10 questions, each with a possible, made up of 10 questions. So we know it's going to be a binomial with 10, and the student gets 4 of the questions correct. So let's start doing all of this now. So let's start by stating our null hypothesis. So our null hypothesis is that the probability is equal to 0.2, saying that she's guessed. Okay. The alternate hypothesis is that the probability is greater than 0.2, and this comes from the teacher who says that, sorry, this doesn't come from the teacher, this comes from the student who says that they're not guessing the answers, okay? So this here is the probability that they guess the answers. This is what the teacher is claiming, and the student is claiming that they're not guessing the answers and they've actually revised, in which case they're going to say that the probability of this is equal to greater than 0.2. Let's just make that really clear. The teacher is saying that they are guessing, they've guessed all the answers and got them correctly, in which case would be a probability of 0.2. The student says that they've revised the test, in which case they think that the probability is going to be greater than 0.2 because they have not been guessing. Okay, so the next thing we're going to do is state the fact that this is a binomial distribution. So we're going to say that x is a binomial distribution. We know that there are 10 questions, each with a chance of getting right 0.2. Okay. Now, the student gets 4 of the questions correct. So this here is what we're getting some marks for. We're getting marks for this top part here. We're getting marks for stating our binomial distribution. We now need to actually look at the data which we've got back. The student's got 4 questions correct. So we're looking here at the probability of x being greater than or equal to 4. And we know that this is going to be equal to 1 minus the probability that x is less than or equal to 3. So we're only looking at the probability here. We're not going to be doing the critical regions. We could do critical regions, but we're not at this stage. So we're going to use our calculator. We go to distributions here, binomial CD, which is 1. We're only looking at one variable, so we just only need to go to the variable. And we're looking at x being 3. Remember, this is less than or equal to 3. We've got 10 different questions with a probability of 0.2. So we're going to be looking at that, and that's equal to 1 minus the probability of this is equal to 0.87913 in this case. Okay, so let's work that out. 1 minus the answer is equal to 0.1209, okay, which is equal to 12.09%. Okay, 12.09%. So with this one here, we stated our significance level was 5%. Okay, so we're saying here that 12.09% is greater than 5%. So there is not enough evidence to suggest that there is not enough evidence to reject the teacher's claim. Okay, which means that they could have guessed the answers. So it means that they the student might not have revised, okay? So there is not enough evidence to reject H0. So the teacher's claim could be true. So the teacher's claim could be true. Brilliant. Okay. So we've used the probability there of this one. Okay. Now we could have also used the critical regions for this, in which case we would have found our critical region to be greater than or equal to, well, what would our critical region be in this case? Let's have a little look. So if I was to do, now that's that question done, we get all the marks for all of that there. I am going to look at the critical regions. So with critical regions, we're looking at 10 with 0.2. So here we've got a distribution, binomial CD. We're looking at our lists. Where are we up to? So 0.2 times by 10 is equal to 2, isn't it? So it could be anything above that. Let's go above 4. Let's go 4, 5, 6, 7, and 8. I could change those if I wanted to. Press AC. Press equals. We've got a distribution with 10. A probability of equal to 0.2. And remember, we're looking for the first time that it goes over. Now, actually, looking at this, okay, the one I've got over here is actually 4. Okay, remember, we're going to go below that. So I'm actually going to change this to, if you look here when I've done it, the first one I've got is 0.9672. So actually I'm going to change this to 3, 4, 5, 6, 7, and then see whether 3 is in that region as well. So AC equals, right, no, 3 is equal to 0.879. So actually, the first time it goes over is this 4, which means that the first one I need to go is above that. So the first one in the critical region is going to be equal to P is greater than or equal to 5. Remember, I go find the first one that goes above my critical, above my 1 minus my significance level, which in this case is equal to 4. And then it's going to be equal to the one above that because it's discrete, which is 1 minus the probability of x being less than or equal to 4. So we don't need this, okay? Remember, this is just the other way of actually doing it. So here we've got 1 minus the probability of being less than or equal to 4. So let's store that is equal to 1 minus 0.967207. So 1 minus 0.967207, which is equal to 0.03279, which is equal to 3.2. 3.28%. So our critical region in this case is anything which is greater than or equal to 5. And because we've got an answer of 4, it means that we can't reject the null hypothesis in this case. So let's just check that. So these are the two options here. I'll make this big so you can see it. So the first method we used was just looking at the probability. So we found that the probability was equal to 12.09, brilliant, which is greater than 0.5. So there's insufficient evidence to reject H0, so the teacher's claim is supported. They've also done on this side the critical regions like we did. You don't need this part, you still get the marks for this. So the critical region for this case is equal to x is greater than or equal to 5. So in which case, because the final sentence here would be because the student only got 4 marks correct, she is not in the critical region. So the teacher's claim is supported because of that. Okay, so we've been looking at the moment just at one-tailed tests, and these are actually how they come up in the A level. we're just going to have a look at one more question, which is a two-tailed test. So let's have a look now at a two-tailed test. I probably would suggest actually having a go at this, examples and these pages, because actually there's some really great questions in that, and it's worth practicing as many of these as you can, because they do come up. Something like this is guaranteed to come up in the A level. But we are going to move. I'm going to move on and have a look at a two-tailed test here. So we've already been looking at tests which are biased in each way. So we're either looking at one end or another end. So basically stating something that you don't believe is true. So I think the coin is biased towards heads, or I think the coin is biased towards tails, or I think that my drug is more likely to save lives, or I think that my drug is less likely to save lives. We're looking at those, but sometimes there are things where we don't know what the outcome is going to be. We just don't think that the probability is true. Now, when we don't know whether it's biased towards one way or the other, what we use is something which is called a two-tailed test. So we're still looking at the data, but we're looking at the top end and the bottom end to see whether any of our test results are in that critical region. So let's have a look at this one then. So I'll make it big so you can see it. Make sure you're getting these down in your notes, because remember, the only way to learn maths is to do it. Over a long period of time, it is found that Enrico's restaurant, that the ratio of non-veg to veg meals is 2:1. In Manuel's restaurant, the random sample of 10 people ordering meals, one ordered a vegetarian meal. In Manuel's restaurant, in a random sample of 10 people ordering meals, one ordered a vegetarian meal. Use a 5% significance level to test whether or not the proportion of people eating veggie meals in Manuel's restaurant differs to that in Enrico's restaurant. So we're looking at here at a few things. Now, this isn't easy. This is tough. We've got to really understand what's going on here. So what we're looking at here is we're looking at two different restaurants. We're looking at Enrico's restaurant and Manuel's restaurant, and we're looking at the amount of veg meals which have been ordered. Now, we actually already know Enrico's ratio and probability. Enrico's ratio for non-veg meals to veg meals is equal to 2:1. So we know that the probability of getting a veg meal in Enrico's is equal to 1/3. Remember, it's ratio there, not just 1 to 2. So probability is equal to 1/3 for a veg meal and that's Enrico's, isn't it? Yeah, Enrico's. Okay, so we know the probability of getting a veg meal at Enrico's is equal to 1/3. So we are going to let P, we need to state this, remember, so let P be the probability, I'll change pens so make sure you can see, let P be the probability of getting a veg meal. Okay, we're saying that P is the probability of getting a veg meal. So let X be, well, X is going to be the number of veg meals that we actually get. Let X be the number of veg meals. Okay, brilliant. So the thing we're going to be looking at now is we need to state what our null hypothesis is. So we're saying here that Enrico's probability is equal to 1/3. We know that. And we're looking at Manuel's restaurant and we're seeing whether the proportions are different. So our null hypothesis is that the probability is both the same in both of them. So the probability is equal to 1/3 in both of them. Okay, that's our null hypothesis. Now, we don't know whether we think that Manuel's got more veg meals or less veg meals. We're just comparing both of the probabilities to see whether they are the same. So in this case, our alternate hypothesis is that they are not the same probability. So the probability is not the same. Okay, so this now is we're looking at a two-tailed test. We're looking at both sides of this. Okay, so probability is equal to 1/3. We know this is Enrico's, and we're testing to see whether manuals is the same as this. This is our alternate hypothesis that the probability is not the same. Okay, so we assume that our null hypothesis is true. Okay, we're assuming that our null hypothesis is true. And then we know that it follows a binomial distribution with, well, how many tests did we do? We did 10 people. So 10 people and a probability. Is that probability 1/3? I'm not going to put 0.3 recurrence. We're going to get something weird there. I'm going to put a third. Okay. So now what we need to do is we need to use the information we've got for manuals, which is the test that he did, which was he had 10 people ordering meals and one person ordered a vegetarian meal. So what is the probability of x being less than or equal to 1? Okay. Now, because this is a because we're looking at less than or equal to 1, we only need to look at the a CD which is below that, because we've already got everything which is below using discrete. So here I'm just going to type in, go to 7, discrete. I'm going to go to binomial CD, and I'm going to look at variable. I know that x in this case is equal to 1. I know that n in this case is equal to 10. So 1 out of 10. And I want to see the probability of this happening if the probability was equal to 1. Now, the way we do this is we write 1 in this fraction button here. So 1/3. Okay? So 1 fraction button. It comes up like a comma. 1 fraction button 3. So it actually then comes up with 0.333. See that there? So we press equals. We got a probability there, which is equal to 0.1040, which means that I get a probability of 10.4%. Now, because we're looking at a two-tailed test, so we didn't know whether it was either end, we've got to split the significance level up. So this is a two-tailed test. Okay, which means that we do 5%, which was into our significance level, divided by 2, which is equal to 2.5 each end. Here. Okay, so we're looking at 2.5 each end. Now, we got 10.4, which is actually massively outside of our critical region. So 10.4 is greater than 2.5, which means that there's not enough evidence to reject H0. So there is not enough evidence to reject H0. Okay, so there's not enough evidence to reject H0, which means that there is not enough evidence to suggest that the proportion is different in manuals. So there's not enough evidence to reject H0. So what we say here is the proportions could be the same. Okay, so the proportions, I should probably say in each restaurant, the proportions in each restaurant could be the same. Okay, so let's just make it really, really clear. We've got our original proportions, which we knew for Enrico's. We're saying, are the proportion in manuals different? So are they just not the same? We know we've got an experiment, in which case we've got the binomial. We know that we've got 1 in 10. Now, you might think, looking at that 1 in 10, well, 1 in 10 is really low, and that's nowhere near this third. So the proportions must be different. But actually, when I do a hypothesis test with a significance level of 5%, actually it shows me that this could happen. And the significance level, we don't actually go into the critical region. The significance level is low enough to say that there's not enough evidence to suggest that the proportions are different. And actually, just because the probability here is low, where it's 1 in 10, actually there's not enough evidence to suggest that it's the other way around. Okay, cool. So let's just check that answer. So there is not enough evidence that the proportion of veg meals at Manuel's is different to Enrico. So the proportions in each restaurant could be the same. Now I've got to say the word could be, because again it's just probability, but there isn't enough evidence to suggest that the proportions are different. Okay, we've got one final question to do on two-tailed test. It is it's a past paper question. Okay, I'm going to suggest that you pause and have a go at this one yourself. Okay. So pause now and have a little go at that. So let's have a look at this one together then. A teacher thinks that 20% of the pupils in a school read the Dino comic regularly. He chooses 20 people at random and finds that 9 of them read Dino. Test at a 5% significance level whether or not there is evidence to suggest the percentage of pupils that read Dino is different from the 20% and state your hypothesis clearly. So notice with this one, they're not saying either way. State all the possible numbers of pupils that read Dino from a sample size of 20 that will make the test in part A significant at the 5% level. So let's have a look at this first part then. So the first thing I need to do here is to state my null hypothesis and my alternate hypothesis. So we're talking about the fact that pupils read a comic book. So our null hypothesis is what the teacher thinks. So the teacher thinks that the probability of this is equal to 20%, which in this case is equal to 0.2. Okay, she's done a test and she's testing to see whether that is wrong. So our alternate hypothesis is that the probability is not equal to 0.2. We're not saying one way, we're not saying the other way, we're just saying that it's not equal to 0.2. Okay. Now, this is why it's quite difficult here, because you've got to be able to say whether they're suggesting towards one thing or another, or a two-tailed test. So this is our null hypothesis, this is our alternate hypothesis. So we should probably say here that the probability, P is the probability of a pupil reading the Dino, okay, and X is a student who reads the Dino. Okay, so we've got here, P is the probability of a pupil reading the Dino, and X is a student who actually reads the Dino. So we've got our null hypothesis, we've got our alternate hypothesis, super. So the next part is we're going to think about our test. So with this one here, we know that she's done a test and 9 out of the 10 people read the Dino. So we know that X follows a binomial distribution of 20 students. Yeah, 20 students. We are assuming at this stage that the probability is equal to 0.2. We're trying to find the probability of 9. So we need to be thinking about here, is 9 greater than or equal to the expected value here? Well, the way I work that out is I'm going to do 20 times by the probability, 20 times by the probability, which in this case is equal to 0.2, so 4. So this is much bigger than what we expect it to be, okay? So here we're looking at, is the probability of X being greater than or equal to 9, which is equal to 1 minus the probability of X being less than or equal to 8. So here we're saying, is the probability of it being greater than or equal to 9, which is what we've got, significantly different from our original probability here? So let's work that out. Now, go to 7, go to binomial, CD. We're only looking at one variable, so let's just click on variable. So we've got x in this case is equal to, I'm going to put 8 in because it's less than or equal to 8, with a number which is 20, and a probability in this case of equal to 0.2. And here I get 1 minus 0.990018 it is. So 1 minus the answer, which in this case is equal to something very small, 0.00998. So remember that this is a two-tailed test. So we're looking at the splitting this our significance level. So because it's a two-tailed test, we do 5% divided by 2, which is equal to 2.5 on each end. However, this is equal to, what's that? 1% would be here. This is equal to 0.998%, isn't it? 0.998%. So here we can say that 0.998% is less than 2.5%, which means that there is significant evidence to reject the teacher's claim. And actually, we do not actually think the probability is equal to 0.2. So let's just make that really clear. So as we have this, as 0.998% is less than 2.5, we can reject H0 and accept H1. So there is significant evidence to say that the teacher's claim is wrong. There is evidence to say the teacher's claim is wrong. So there's enough evidence to say that the teacher's claim is wrong. Okay, so that was part A. So part B says, state all the possible pupils that read the Dino from a sample size of 20 that will make the test in part A at a significant level of 5%. Now, remember that we need to look at here both sides of the tail. Now, what this is asking for, it is asking for those critical regions. It's saying, what are the critical regions of this that will give me, or what are the sample sizes that will give me a sample size at 5%? So we need to here look at the list of all of these. We need to see what in my list is going to give me this significance level of 5%, 2.5% at the top end and 2.5% at the bottom end. So we're looking at two things here. So let's get our list up. Now, we already know that anything which is greater than or equal to 9 is in the critical region. So that's a good place to start at the top end. But don't forget, we're also looking at the bottom end, so looking at below 2.5. So because it's a two-tailed test, remember, this is for part I now. We're doing 5% divided by 2, which is equal to 2.5%. So we're looking for the first time that we go below 2.5%, and we're looking for the first time that we go above 2.5%, and then we're going to be doing one above that, remember. So this is what we're looking for here in our list. So what I'm going to suggest is we're going to start at 0. I'm going to do in my list, let's go here. Remember, it's a binomial distribution with a size of 20 and a probability of 0.2. Okay, that's what we're doing here. So we go to distributions. We're going to go to binomial CD in this case. We're looking at a list this time. Okay, I'm going to start with 0. I'm probably going to do 0, 1, and 2 for the bottom end. Okay, remember we're looking for the, put 0, 1, and 2 in there. We know that 9 is in the critical region because we've just done a test for 9. It's probably worth testing 2 below that, so maybe 7, 8, and we already know 9 is, but I'll do it anyway. Okay, so press AC, press equals. We've got 20 people from our test. We know that we're testing this for a probability of 0.2. So let me write down everything that I've got here just to make it really clear. So remember this is less than or equal to. So here, when x is less than or equal to 0, I've got a probability which is equal to 0.115. When x is less than or equal to 1, I've got a probability which is equal to 0.015. So that should be 0.0691. When x is less than or equal to 2, I've got a probability which is equal to 0.206. Now, then I moved on to 7, didn't I? So when x was less than or equal to 7, I've got here a probability which is equal to 0.9678. When x is less than or equal to 8, I've got a probability which is equal to 0.99, and when x is less than or equal to 9, I've got a probability which is equal to 0.9974. Now remember, I'm looking at 2.5 on each side, so the bottom is going to be less than 2.5. So anything which is, I'm looking for anything which is less than 2.5. In this case, I'm looking for things which are less than 0.025. So anything which is below that. But I'm also looking for the one above, remember, because it's discrete, 1 minus that. So 1, then 1 minus 0.025. So I'm looking for the first time that I go above 0.975. Anything above that and anything below that. Well, let's have a look at this one here first. So the first one that goes below this in our critical region is, that one's not. 0 is included in this. So actually, 0 is in our critical region. So x is less than or equal to 0 is in that critical region, yes. So, when's the first time I go above 0.975? Well, this one isn't, but this one is. And remember, I go to the next one because I'm doing greater than. So this one here is brilliant. So it's the probability here of, I should probably say here, probability that x is less than or equal to 0 is equal to 0.0115. The probability that x is greater than or equal to 9 is 1 minus, is equal to 1 minus the probability that x is less than or equal to 8. In this case, that's equal to 1 minus 0.99, which is equal to 1 minus 0.99, 0.01. So actually, we know that the first one in the critical region is anything which is greater than or equal to 9. So which values will give it me? Well, we know this is only up to 20. So it's anything where x is less than 0 or 9 is less than x is less than or equal to 20. So if I was to get 0 in my test, then I know that this hypothesis is wrong. Or if I get anything between 9 and 20, then I know this hypothesis is wrong as well. So we know that, remember, we've already got one of those. We did a test in that part A, but this is the answer to that part B. Okay, so let's just have a little look at that. Let's check what we've done. So here, because we got 9, okay, there is evidence that the percentage of pupils that read Dino is not 20%. So we rejected H0 and accepted H1 in this case. Okay, so in part 2, we've done a binomial and we've got to test them. Now, they haven't actually showed you any of this here in this working, okay? But this is the kind of thing that you need to do. So you need to be finding the first time it goes below 0.025. We need to find the first time it goes above that. In this case, it's going to be 0 in this case, this one here. And we go 1 above in this case. So this is the first time that it goes above this one. But remember, it's going to be 1 minus that, okay? So we do 1 above. So our regions here are 0 and between 9 and 20. Now, they wrote that with a bracket, but you can write that. So anything which is less than or equal to 0, I should probably just put 0 in that case because we can't get anything equal to 0. So when x is equal to 0 or x is between 9 and 20. So look, we're getting 4 marks for that, okay? So 9 and 20 and 0 as well. Brilliant. And that's that question done. And that there actually is the end of hypothesis testing. That's the last question in this. Again, I'm going to suggest that you do this exercise because they are tricky and they will come up, all right? You need to do lots of practice on this. You will need to, I've only done a few examples and I know it's taken me quite a long time, but these questions will come up exactly like I've just taught. They are tricky, so do make sure you're having a go at them. Remember, the only way to learn maths is to do it. So thank you for watching this video on hypothesis testing. Do practice them. Do have a go at them. They are tricky, but have a lovely day and thank you for watching.